Welcome friends to EPG Pathshala lectures on numerical methods module 4. In this module we will be taking the second part of Newton's divided difference interpolation. If you look at the learning objectives, we will be talking about Newton's divided difference interpolation polynomial algorithm and the time complexity of this algorithm, and we will be also discussing the interpolating error in the context of Newton's divided difference interpolating polynomial. If you look at the last time in the last module, we introduced divided differences and Newton's divided difference interpolation polynomial, and we have also seen some of the illustrations. In this module, we will be talking about this algorithm, Newton's divided difference interpolating polynomial algorithm, and its computational aspects will be discussed. Also, interpolating error in the context of Newton's divided difference interpolating polynomial will be discussed. If you look at the algorithm, our normal style of presentation of the algorithm is we talk about what is the input to the algorithm and what will be the output and what is the iterative procedure that is following. So, input to the algorithm here we have to give as the n, the degree of the interpolating polynomial, or the n involved in the n plus 1 data points. Then data points themselves x I, y I for I equal to 0, 1, 2, 3 up to n, and such that x 0, x 1, x 2, x n are distinct and x belongs to a b, where a is the minimum of all these nodes and b is the maximum of all these nodes. So, we are taking these nodes not necessarily in the increasing order, but they are within the interval a b. Like that we are taking nodes, these nodes are taken as input. The output of the algorithm will be the value of the interpolating polynomial at the x, and the value of the nth degree divided difference polynomial over the given data points, and value of the coefficients a 0, a 1, a 2, a 3, a n. So, this is what we will be doing. So, p x is the value of the nth degree divided difference polynomial over the given data point and value of the coefficient a 0, a 1, a 2, a 3, a n. So, that will be the output. We need to initialize the algorithm here, and initialization of the algorithm will be done as per I. For I equal to 0 to n, we have to initialize. So, we are first initializing 0th divided differences. As you know that 0th divided differences are nothing but the values of I only, and only I, and a 0 is given by f x 0. So, that means the first coefficient of the polynomial a 0 is given by f x 0. P x is initialized to a 0 because we are computing this p x value by iterative procedure of summation, and so first term in that summation sum will be a 0, and then we will have here t equal to 1. So, t will be the term in that interpolating polynomial the representation. So, this is the term, this is the first coefficient a 0, this is your y I is the initial values of all the 0th divided differences, and p x also initiated as a 0, and subsequently we will go on adding the terms to p x in order to get the final value. So, these are all initializations we are talking about. Now, the iterative step gives me here like this, that for I equal to 1 to n and for j equal to 1 to n, first I am computing divided differences. So, for I equal to 1, I will be computing all the divided differences of order 1 from for I equal to 1 to so I 1. So, this will be also 1 to n. So, n divided differences will be computing, and the formula is straightforward, which is given in general. So, this is the general formula for divided differences. So, we are getting this, and then corresponding A I will be represented by the divided difference, this x 0, x 1, x 2, x I. So, I will be getting A I as this. So, I equal to 1 will give me A 1, and that will be f x 0 to x 1. I equal to 2 will give me A 2 f x 0 x 1 x 2. So, I am first calculating column by column all the divided differences. Once the column is over, I am taking the coefficient A 1, A 2 and all those things I am doing. Now, the term of the polynomial that we are considering is initialized already to 1. So, t is 1. So, in the first case I will be getting t I equal to 1 if I write, this will be t equal to 1. So, 1 factor will be multiplied to the term, that is x minus x 0. In the second evaluation of the for loop, I will be getting I equal to 2 and term will be multiplied by the second factor. So, that is how the term will be modified in the subsequent iterations. And the p x I am getting. So, this is modified when I equal to 1. So, I will be getting p x initially is a 0, then I will get a 1 into t, t is 1, a 1 into t, t is given by x minus x 0 this factor. So, I will be getting f x 0 into x minus x 0 as a factor. So, that I will be getting the 2 terms of the p x added. Then y is equal to 3, I will be getting 3 terms added to that, and so on, like that we do. So, when the loop is executed, I will finally get the value of output p x. So, this output p x I am storing it as p n x just to indicate that this is nth degree approximation. So, nth degree polynomial approximation to p x, and the coefficients a 0, a 1, a 2, a 3, a n if I give you the form of the Newton's divided interpolating polynomial you know. So, we can write down with this coefficients the Newton's divided difference interpolating polynomial. So, we consider the iterative step in the algorithm NDDIP. So, iterative steps is nothing but the computation of the p x and all that we are doing. So, it will be written by for I equal to 1 to n, and there will be double for loop here. For j equal to 1 to n, I to n, we are computing first divided differences. So, first column of the divided differences will be computed as when I is equal to 1. So, that is all first order divided differences will be computed, because if I take I equal to 1 and j equal to 1, then I will be getting here 0 and 0 1 x 0 x 1. So, I will be getting first divided difference of the order 1, and subsequently I will get remaining ones. Now, the first divided difference is nothing but a 1, value of a 1, we have already seen that, and therefore, I am writing a I as the first value of this computed in this particular loop, j loop. After that, I am modifying my term of the polynomial p x. The term earlier it was taken to be 1, initialized to 1, and when I is equal to 1, I will be getting term as 1 into x minus x 0. So, I will be getting factors x minus x 0 factor will be multiplied to the term, and then you will get p x up to 2 terms added. So, p x earlier value of p x is a 0. So, that is a 0 plus a 1 into x minus x 0, that will be first 2 terms of the polynomial will be added, and when I equal to 2, the third term will be added to the polynomial, I equal to 3, fourth term will be added, and so on so forth. So, we will be getting the once all both these for loops are executed completely, I will be getting the value of p x. The output is nothing but we get p n x, I am storing that value in p n x, that is it, nothing else, to just indicate that this is nth degree polynomial approximation. And coefficients of the polynomial we are considering as a 0, a 1, a 2, a 3, a n. So, these are the coefficients. Once I give you this coefficient, we can easily write down the polynomial, because the form of the Newton's divided difference interpolating polynomial is already known to you. Then we talk about the time complexity of this algorithm. So, if you look at the time complexity, we are, as we have already indicated in the earlier modules, the time complexity is measured in terms of the arithmetic operations performed during the execution of the algorithm. And the arithmetic operations mainly we divided into 2 groups, addition and subtraction, multiplication, division. because they are taking almost the same time, and we calculate how many additions or subtractions being done and how many multiplications are done. So, that is how we are computing in the algorithm. If you look at this particular algorithm, you can see that the divided differences, when you are trying to evaluate, there are n into n plus 1 by 2 divided differences. Why? Because the first divided difference we compute, there will be n first divided differences, then n minus 1 second divided differences, and so on. So, n plus n minus 1 plus up to 1. So, 1, and that sum will be nothing but n into n plus 1 by 2, and therefore, total divided differences computed will be n into n plus 1 by 2. Now, if you consider each divided difference requires one subtraction, because you have to subtract the numerator, and one division operation. So, that is what you have to do, and in addition n multiplication and n addition are required to compute the p n x, and hence the time required for our time complexity for this particular algorithm will be nothing but n square plus 3 n into a plus m by 2. A plus m by 2 we are considering, this 2 comes from here. So, n into n square plus 3 n divided by 2 into a plus m, that is what we can say. Thus, the time complexity you can see here that it is nothing but order n square. So, asymptotic time complexity will be order m square, because we ignore the constant values here, and how it relates to size of the problem. So, that asymptotic complexity will be given by order n square. Now, we compute the error of interpolation. So, since there is a unique polynomial of degree less than or equal to n passing through the n plus 1 data points x I y I equal to 0 to 1 is 0 to up to n, the interpolating polynomial obtained by Newton's divided difference interpolation formula over the given data points is same as that in the Lagrange's interpolating polynomial over the same data points, and hence the interpolating error E x in this case is also given by the same formula E x equal to f n plus 1 into z x is any point in the interval a b and so on, upon n plus 1 factorial into product of these factors x minus x 0, x minus x 1 into up to x minus x n, and the z x is some point in the interval open interval a b, where a b is the domain of observation. So, a will be the smallest observation, b will be the largest observation. If we can in fact verify this, that the formula for error is given by this, by using properties of the divided differences, and that can be done like this. What we do is observe that you know p k plus 1 x. So, if I consider now, what I am going to do here is I am going to add to this data points, I will be adding one additional data point here, and x and f x, and what we will do is, so p k plus 1 x can be expressed in the form of this, that we can observe first. So, observe that k plus 1th degree polynomial p k plus 1 x is expressed in terms of p k x and the last term that we add additionally. So, that is f of x 0 up to x k into this k factors, where p k is denoted by the kth degree divided difference interpolating polynomial over first k plus 1 data points x I y I equal to 0 1 2 3 up to k. Now, given n plus 1 data points and x in the domain of observation, what we will do is we will add n plus second data point x f x to this set of points, then p n plus 1 x will be given by p n x plus, now I will get this is the last observation that I am going to make here. So, x 0 x n up to x into, now the last factor will also be added x minus x 0 x minus x 1, and I have to go up to x n. In earlier case we have earlier term we have x n minus 1 we were considering here, but because we have added additional point here I will be going up to x n. So, these are the factors I am going to get. So, I can represent p n plus 1 x in this format like this. So, what I am trying to do is I am assuming that additional data point I am adding to my already given data points. and that additional data point I am considering as x f x, that is the last node I am considering. So, using that I am finding out p n plus 1 polynomial, p n plus 1 degree polynomial, and that will give me p n plus 1 x will be like this. And because x f x is one of the data points, this is the additional condition I have to put, that p n plus 1 x must be equal to f x. So, that is the additional condition we have to put, as this becomes one of the observed data points. Now, what we do is then we can compute the error. So, what will be the error now? E x, you know that E x is given by what? F x minus p n x. So, f x is given by p n plus 1 x. So, if I use that, I can see that f x will be given by, if you look at the previous slide, you know that p n plus 1 x is given by this value. So, p n plus 1 x, where we have written down here, p n plus 1 x equal to p n x plus this into this value. So, we are getting now p n plus 1 x will be f x. So, f x minus p n x will be error, and that error will be given by simply this term here, final term here. So, we get here error as the final term, which is given by this. Now, if you observe the property 3 of the divided differences, you know that this n plus 1th divided difference will be given by n plus 1th derivative of f x z x into n plus 1 factorial, and this z x will be some point in the open interval a b, where a closed interval a b is the interval of observation. So, therefore, this formula can be justified using Newton's divided difference interpolating polynomial and the properties of the divided differences. Now, we consider the illustration, and in this illustration again we are going to consider the same function as we have considered in the Lagrange's interpolation, and we will see how the error can be computed for Newton's divided difference interpolating polynomial. So, I am taking, let f x be equal to e raised to 2 x into cos 3 x for x belonging to 0 to 1. Find the approximate value of f of 0.5. Now, we are finding out a value of f of 0.5 using Newton's divided difference interpolating polynomials of degrees 3 over the nodes x equal to 0, x equal to 0.3, x equal to 0.6 and x equal to 1. We can also find this approximation using other degrees, I mean lower degree polynomials of Newton divided difference polynomials. Also compute the actual error E 0.5. So, this is also I want to find out, because actual error I can compute, because I know the form of the function. If I do not know the form of the function, I cannot find out actual value of the error. So, first we need to compute the Newton's divided difference interpolating polynomials, and for that we need finite, I mean divided differences of all the orders, and that is how I am doing now here. So, these are my observations x I. So, 0, 0.3, 0.6, 1, and last observation I am writing it as 0.5, because you know that we have taken n plus 1 data points here. So, 0.5 I am writing here, f x I am writing from here, the f x I at 0. So, if we put the value in the given function, I will be getting these values. So, put x equal to this in the given function, and what is that given function? E raised to 2 x into cos 3 x. So, in that function I am putting value of x equal to 0, I will get 1, x equal to 0.3 I will get this value, x equal to 0.5 I will get this value, and so on and so forth. And then we are finding out all these differences. So, differences I am finding it as this minus this divided by this minus this. So, we have already done such exercise earlier. So, you can compute this divided difference table, and then we are now considering the value of f 0.5 using third degree Newton's divided difference interpolating polynomial. So, third degree Newton's divided difference interpolating polynomial, as you know that we will be using these values from the table. So, these values will be used from the table, and that is what we are doing here. So, I am getting 1.0 plus 0.4422 into 0.5, because that is my x value. So, x minus x 0, x minus x 1, like that I am getting. So, So, this is x minus x 1, 11.22 and 3.226 into this 3 factors, and if you simplify you will be getting value as 0.13136. Exact value of f 0.5 as we already computed earlier in the table, and that is equal to 0.19228, and hence the actual error we can compute as difference of these two, and that is 0.06092. Formula for error yields. Now, if you use the formula for error, that will be using this divided difference, which includes 0.5 as my nodal point, and therefore, I am now going to take the last value from the table as my value of this divided difference, and that is given by what? If you observe, this value is given by 12.212, and that value I am using here. So, for this I am using this value and then remaining factors, and if you simplify I will be getting 0.06106. So, by formula I will get error this much, and actual error is slightly different than that, but that is only because of certain results. Small difference in these two values is due to round off errors involved in the computation. So, because of computations there will be round off errors introduced, and because of that there will be small error here. If we estimate y 0.5 using quadratic interpolating polynomial over 0.31, 0.321, and then I will be getting this will be 0.5, I will be using the corresponding differences, divided differences. So, accordingly I will be getting 1.13265 into this minus 6.29 into 0.5 minus 0.3, and that is how I will be getting. Why? Because I am going to use this interval. So, in that interval how many data points are there we have got? If you look at the table you will see that 0.321. So, there are 3 data points 0.3, 0.6 and 0.1, and I will be using these values this and like that. This value will not be using, but these 3 values will be using, and these are the 3 values seen in the expression there. So, we are considering here this expression for quadratic polynomial. So, that is 1.13265 minus 6.29 into this minus 14.446 into this and on simplification I will be getting 0.16357 as value of my y 0.5 approximated using quadratic interpolating polynomial. And similarly, we can do, and in this case error will be 0.02871 because actual value minus the estimated value. So, that will give you this. Now, which is the less than the error computed using the third degree polynomial. So, third degree polynomial we got error little more, and in the second degree polynomial we have got error little more than that. So, it is not necessary that higher degree polynomial will always give you better results. Now, exact value of 0.5 is this, where as estimated value of a p 3 point this is 133, therefore, E 0.5 is this much. So, exact error we have got. Note that by quadratic interpolation over interval 0.31 gives better approximation as the error is 0.0287. One can compute, see if we want to get the estimate of the error, then we have to use that error formula, and in this case I can find out the fourth derivative of the function f x. It will be like this, and if you see that hence E x will be less than 239 point E square by 4 factorial. If you substitute these values here, absolute value when you take will be added, and you will be getting 239 from here, this plus this that is added, because these values are going to be close to 1, and maximum value will be 239 into E square divided by 4 factorial, which turns out to be 73.58, which is a very crude figure, and therefore, these estimates are not that good for using them into numerical computations. You can see that error is roughly of the order 0.06, 0.02 and so on and so forth, whereas our estimate says that error will be less than 73.858, and therefore, this formula only gives you very crude kind of bound on the error. Now, if you compare various polynomials here, we can see that this is the linear polynomial on this interval, then there will be quadratic polynomial, green quadratic polynomial here, there will be this another quadratic polynomial blue, and then there will be cubic polynomial, and this is the original curve. So, we can all the comparisons are given over here in the on the whole interval, but we can find out this on the small interval where all the 4 polynomials are available, and that will give me a better idea as to how these values compare with each other. And these are the 4 estimates that I get for the given value. So, this is linear, quadratic, another quadratic polynomial, cubic polynomial, and original function. So, these are the various values we are getting. And graphical comparison, if I consider, because now I have got 2 interpolating formula, Newton's divided difference interpolation and Lagrange interpolation formula. So, I am just trying to compare both of them. You can see that I am able to see only 2 graphs here. One is the original one and another is the blue one, because these 2 Lagrange as well as Newton's divided difference interpolating polynomial, both these curves coincide with each other, and therefore, only 2 graphs are seen in the figure here. So, both these formula give us the same interpolating polynomial. So, in this module what we discussed is the Newton's divided difference interpolation algorithm. Then we discussed the time complexity of this algorithm, and we discussed the error in interpolation in the context of Newton's divided difference interpolation. We have also seen some of the illustrations comparing the various degrees of Newton's divided difference interpolating polynomial and comparison between the Newton's divided difference interpolation and Lagrange interpolation polynomial. Next, in the next module, probably we will be considering the equally spaced nodes, and we will see what kind of interpolation formulas or interpolating polynomials we can derive on the basis of equally spaced nodes in the next module. Thank you.